Yep.
Can people hear what I'm saying? Or
You're good.
Yep,
okay,
you're good.
great, awesome. So I just want to get started with similar to last week where we asked you about the util lab. I just want to get started by asking a little bit about syscall lab since that was due on Thursday. So if anybody just has like something particularly interesting they found about the lab or a nasty bug that they found or just a silly mistake they made, anything you want to share about the syscall lab, that'd be great.
I somehow managed to delete the part from from fork where you have to copy over the mask. So I had that working, and then I changed something else, and then I tested it.
Sorry, I don't know if your audio is like cutting out, I think.
Oh, it is? Sorry. You hear me? I hear you. Oh, okay. Yeah, I guess. So basically I deleted somehow the copy of the mask, and then my fork didn't work anymore. So then I was just like, I did that. How does it not work? So spend a lot of time figuring out what I did wrong. And I realized I just deleted that line somehow.
Yeah. Is anybody having trouble hearing Luca, or is that on my end?
I think it's on your end.
Yeah, I hear him fine.
This must be on my end. Sorry, maybe that'll work better now.
Can you hear me now?
Yes, perfect.
Okay, great. I was worried that I was just talking to the
No. Seems to be on my end.
All right.
Awesome. Well, anybody else have anything they'd like to share about you or syscall? Anything particularly interesting, or was the lab absolutely horrendous and you think we should cut it out of the class? Never do it again.
I have something.
Yeah.
Apparently the order of things matters, which is a general statement. So I tried to determine the mask computation inside the syscall function before determining whether I actually needed to do the tracing. And so all the syscalls were getting correctly traced except the trace call. And I was really getting disturbed by that until I think it was David who pointed out, you should do the computation after you should trace. So it's like, that's smart.
I'm glad you were able to catch that. Yeah, order does matter, especially for page tables. You'll find, I think, that order matters there as well, and generally throughout the class. Paying attention to the order of things will be important. It's good to not overwrite things in page table.
I also had something which I'm actually still confused about. While I had a lot of debugging print statements in the kernel code, I then ran the trace thing with all of the bits set. So basically tracing all the system calls. And I think I saw a lot of tracing for the print statements in the kernel, and then I assumed that my printfs were trying to read and write to the console, but then I was wondering, why are we? I guess I'm just confused why we're able to use printf in the kernel.
Yeah, I haven't looked at the printf code recently, but I think there's a file, printf.c, that you might be able to look at if you want to figure out what was going on there. So I think the printf function should be implemented in there. At least our version of it. I don't know, perhaps one of some of the other core staff might know what's going on.
Yeah, the printfs in the kernel shouldn't show up as in your traces, because printf in the kernel doesn't call any system calls.
So, yeah, that's what I thought. Maybe then maybe the tracing was not from that.
Yeah, I don't think it is from your printfs in the kernel.
Okay.
Okay, well, unless anybody has any other burning comments about syscall, I think we can get started with lecture for today. We'll be talking a little bit about the process of converting C to assembly and processors, and this is more of kind of a practical lecture today, or at least that's the aim. So the goal here is to get you all familiarized with RISC-V, the processor, the assembly language, and the calling conventions for RISC-V. And this will be important in not super important for a page table, but certainly for the traps lab, which will be assigned later this week. This will be essential for debugging and implementing things because you'll be working quite intimately with trap frames and the stack and things like that. So that's kind of the goal for today. And my first aim was to, and this might be a little bit of review from 6004 or any other computer architecture theme classes that you may have taken in the past, but I just want to go over briefly kind of C, the C language, how we get to assembly, and maybe a little bit about processor. So throughout, and then of course throughout this lecture, feel free to interrupt with any questions that you have. So, we have our normal main functions in C. They do something, maybe they print something, then they exit. And this all looks well and good, but as any of you are aware from 6004, processors don't actually understand the C language. Rather, they understand what we call assembly, or more specifically, they understand the binary encodings of assembly. And so this here, I've circled a picture of an actual RISC-V processor from a Sci5 board. And when we say a processor is RISC-V, that means that it understands the RISC-V instruction set. So every processor has an associated ISA or instruction, and that's kind of the set of instructions that makes sense to that processor. So every instruction has an associated binary encoding or an opcode. And when a processor is running and it sees a particular encoding, it knows what to do. And so, this processor on this board happens to understand the RISC-V assembly, which is what C code is compiled to. So the general process of getting C code to actually run on your processor is we start with C, it gets compiled to assembly, and there's some linking and things like that happen between the step, but we're not a compilers class. So, and then the assembly will then be translated into binary. And so this is the object or .o files that you see. So if you've ever paid attention to what's inside of your lab directory after you run makeqmu, you'll see a bunch of .o files lying around. And those are the actual object files that the processor understands. And the ASM files you've also seen, you haven't really written any, but if you recall from syscall, usys.pl is compiled to a file called usys.s. And so .s files are assembly language. And so you've certainly seen some RISC-V assembly, and if you took 004, I believe you've also seen a good amount of assembly language. And assembly looks, in general, much less structured than C, so you'll just see lines after line after line of instructions. You'll see simple things like add, mult, etc., and so on and so forth. And this there's no nice control flow, there's no loops. There are functions, but not in the sense that you might remember, from C. We see labels as opposed to true function definitions. And assembly, so it's a much lower language, and there are plenty of other languages that are also compiled to assembly. So the same process holds true for things like C++. Any language that's compiled will go to the same assembly language at the base. And And so that's kind of the basic process of getting our computer to actually understand the C code that we're writing. But you'll notice that we've been referring to RISC-V assembly throughout the course, and the processor is RISC-V. And that's because it's important because there's many different kinds of assembly. So it's unlikely that you're using RISC-V yourself, like you're not going to be running Linux on it. Instead, most modern computers will run on what's called x86, or you'll sometimes see it as x86-64. And this is a different ISA. This is a different instruction set. It looks pretty similar to RISC-V, but this is what you see in kind of your personal computers often. So if you use an Intel, so Intel CPUs implement x86, and I believe AMD also do. And this is a relatively important distinction between the two. They're not quite as similar as they may look at first. And that comes down to the fact that RISC-V is what we call, the RISC part of RISC-V refers to a reduced instruction set. And x86-64 is what's called a CISC, or complex instruction set. And there's a couple of key differences here. One is just the number of instructions that are present in x86-64. In fact, one of the big motivations for writing, for making RISC-V was how many instructions we actually have in the Intel kind of handbook. So for reference, there's 3 full books that encompass the ISA and some statistics. I think there's new instructions have been added at a rate of 3 instructions per month since x86-64 was added. It was first published in the 70s. So I believe there's like north of 15,000 instructions in x86-64. And RISC-V, on the other hand, the assembly for RISC-V can be nicely contained within 2 documents. And so kind of going off of that, we don't expect you in this course to memorize every single RISC-V instruction, but if you are interested or you ever find yourself confused by what a specific instruction is or does, if you go to the course website and we look under the references tab, under RISC-V, we give you the links to both the privileged and unprivileged instruction sets. So this is kind of the document that gives you a whole bunch of information about the ISA, but you'll note that like this is 240 pages and this is 135 pages. So it's significantly smaller than the x86 instruction set. And that's one of the nice things about RISC-V. So we have, in RISC-V, we have fewer instructions, and not only that, the instructions are simpler. So what I mean by that is that there are many instructions in x86-64, and by instruction I'm referring to something like add or mult or sub. In x86-64, there's plenty of instructions that do more than one thing. So they perform some complicated set of operations and then get you the result, and that's not the case with RISC-V. RISC-V instructions tend to be smaller in scope, and so they take, it's less cycles to run each instruction than maybe x86-64 is, and this is just a trade-off that the designers chose to undertake. There's nothing, or there's no canonical reason why a reduced instruction set is better than a complex instruction set. They each have their own uses, and so on and so forth. And another cool thing about RISC-V as opposed to x86 is that this is open source. So it's one of the only open source instruction sets on the market. So that means anybody can develop a board for RISC-V. and it came out of a research project from UC Berkeley, and so that's kind of where RISC-V started. And since then, it's been picked up and supported by a number of companies. You can find the list online, but there's tons of big companies that are interested in supporting an open instruction set. And actually, I think quite recently there was an announcement made by Sci-Fi, who are sort of the premier board manufacturer for RISC-V processors, that they will be releasing a board for personal computers that should ostensibly, a RISC-V processor designed to run Linux for personal computers. And I think that that's been released in the last week or two, the announcement about it. So if you're curious, if you find yourself, absolutely, I want to use RISC-V after I finish 6S081, hopefully by that time there will be a processor available that you can run Linux on your own computer. But even in your day-to-day lives, you're most likely using reduced instruction sets, even if you don't realize it. So the ARM assembly, so that's ARM, this is also a reduced instruction set. And ARM is implemented by Qualcomm, the Snapdragon series of processors. So if you have an Android phone, you are most likely running a reduced instruction set. And even if you're using iOS, I forget what the name of it is, but Apple has some version of ARM that they also implement in their own processors that runs on iPads, iPhones, and most mobile Apple devices. So, reduced instruction sets are present all over the place. And if you're looking for RISC-V in the real world, outside of your QEMU, you'll be able to find that in like integrated devices. So it is present. It's certainly not as ubiquitous as something like x86-64, but yes. I think Apple is, as Lucas just said in the chat, I think Apple is moving Macs to ARM. I believe that's also the case. There's been, in the last few years, there's definitely been a push towards reduced instruction sets, given how big the Intel ISA has gotten. And the reason why Intel's ISA is so big is because they're very concerned with backwards compatibility. So if you write, a modern Intel processor can run the same instructions that Intel code from 30, 40 years ago was written in. So they don't really deprecate any instructions so that they maintain backwards compatibility. And RISC-V is more modern, so that's not a worry. RISC-V is also, so if we jump back to those manuals, RISC-V is unique in that it's divided. We have what's called the base integer instruction set, which all RISC-V processors, if we have, so Gabriel asks in the chat, if we have 15,000 instructions, is it nearly impossible to efficiently pipeline them? Why do we need so many? Like I was saying, we need so many for backwards compatibility reasons. It's up to you to decide, whether you think that that's super important, but many of those instructions, I think a ton of them are also eaten up by SIMD instructions, which are their own kind of special class of things. You won't, I've never seen Intel assembly code that makes full usage out of the 15,000 instructions. But mostly this comes from a need for backwards compatibility and SIMD. But like I was saying, so RISC-V has what's called the base integer instruction set, which contains all of the normal add and multiply things. And then processors can choose to implement a number of other modules, which you can see along the side here. It's probably impossible to read on your screen, but for example, if you want a processor that supports standard extension for single precision floating point, then you can include the F module. And this makes it easier for RISC-V to support backwards compatibility, because if you can just say, what set of the modules do I include and support, and the compiler can choose then, the compiler can say, okay, this processor is telling me it supports these modules, so I can only compile this code with these modules. Okay, Bibic says, it seems that the only advantage of using x86 instead of RISC-V processors is the kind of performance you can get. However, that performance comes as a massive cost and complexity and potential security. My question is, why are we still using x86 instead of moving to something like RISC-V? Well, the big answer to that is the world has run on x86 for So I don't have a great answer for why. RISC-V is pretty modern too. So the world as a whole pretty much runs on x86. So if you suddenly start converting your processors to RISC-V, you run the risk of losing support for a bunch of important things. Also, there are Intel does do interesting things within their processors, like security-wise. There are enclaves in Intel processors, and there's things that they've been doing in recent years to try and give you extra added security. And some of those instructions that Intel does implement, which are hyper-specific, can be really efficient for certain computations. And so they have so many instructions that there's often, a perfect instruction for a situation that may be more efficient than what exists within RISC-V. But a more practical answer is that RISC-V is relatively new, and we just don't, nobody's really making processors for personal computers. I think the Sci-Fi announcement is super recent, and they're kind of the first people to be doing that. So on a practical level, that and the inability to run all the software designed for Intel is my best answer. So we've been now chatting a little bit about assembly, so I just wanted to take a look at some actual assembly code. So here is the C code for what's below. So this is a simple function that has an accumulator. We loop from 0 to n, and we sum up all the numbers from 0 to n, and then return that value. And at its simplest level, this is the easiest kind of assembly that you can get out of compiling that program. If you actually go into your own computer and you write the C code and you try to compile it, you will end up with something that likely looks quite different. And that's true for a variety of reasons. We haven't, some of which we'll get to, and some of which are compiler specific. So modern compilers make a large number of optimizations when they compile your C to assembly, and so your assembly instructions may look different. For instance, while you're debugging in GDB, you may come across something that tells you that it's some variable has been optimized out, and that means that the compiler decided it didn't need that variable, and so that'll be gone effectively from the program. But yeah, at its most straightforward, we're moving the value that's in A0 to T0. We're setting A0 to 0, and then we are just adding what's in T0 to A0 for every iteration of a loop until T0 reaches 0. And that's all that's going on in this piece. Amir, your hand's raised.
Yeah, I was wondering what .section, .text, and .global do.
.global means that you can include this from other files. So if we actually hop into, let's see, defs.h. So this is the file that you're if you aren't already, you will become quite familiar with. This includes basically all of the functions within the kernel that you may want to be using. And within here, we can see that in my file, I've included the definitions to these functions. And so that .global makes sure that that these functions can be called from other places. And .text just says this is code. So if you recall from figure 3.4 in the book, so that's if we go to the book, and we go into page tables, process address space. So in here, in this diagram, that's the same thing. This is text, so it just means code. Does that answer your question?
Okay, thanks.
And so if we want to run, let's say we have some assembly. Also, if you ever find yourself interested in what the kernel looks like, we can go inside after you compile, you can look in the file kernel/kernel.asm. And this is the full kind of assembly for the kernel of x86. And each of these numbers on the left here is a label that tells you where in memory this instruction will be, and that'll come in quite handy. And so here's the actual here's the actual assembly code, and you can see the labels for the functions and where they're declared. So this can be really, really useful as we're debugging code, and hopefully I'll be able to show that in a second. But for now, we'll jump back to this first function, sum2, and we'll just see how we can examine that inside of GDB. So the first step is I have my two windows here. What's the difference between .asm and .s files? I'm not 100% certain. They're both assembly. I think the .asm file includes a bunch of extra annotations that aren't included in .s. So usually when you compile your C code to .s, you'll end up with something that doesn't include all of those line numbers and things like that. So if you're curious about how we get the .asm file, I think the make file will tell you the exact steps used to get that. And so if we're in our terminal, we have our two windows. So the first thing to do is, of course, get QEMU up and running. So we can start it within GDB mode. So now we're frozen here, and then we can start GDB. And what Professor Kasha showed last week, which I think some people were excited about. If you type TUI enable, you get this nice window, which is empty for now, but will come in quite useful as you're debugging. So we can set a breakpoint, and I should note that all this code is living inside the kernel. None of this is in user space, so we don't have any of those annoying problems setting breakpoints. So I can set a breakpoint in the function sum2, and then just continue running. And run that function. And now, so the first window that you see in TUI is the source window. Yes, as David is saying, those numbers on the left of kernel.asm are really useful when you're debugging things and you get an address. It'll tell you. So you can see now, even here, we can see that the program, so PC here in GDB, is the program counter. So we can see this address, 800, so on and so forth. If we go into kernel.asm and we search for that specific address, we can see that it's the, well, it comes up twice because it's a function call. But if we look here, this is that address. It's the top of the sum2 function. So if you see, anytime you see one of these, all the kernel addresses will look something like 0x8000, some numbers. Those addresses, you can jump straight into kernel.asm and find the exact line of assembly where the problem is occurring, and then you can set your breakpoints accordingly. But for now, that top window in TUI is the source, and if we want to look at specifically the assembly, we can do layout in GDB ASM, and that'll give us all of the assembly instructions. And we can also look at the registers. If we type layout reg, we'll get assembly and registers. And if you find yourself, wanting to scroll through things, now that we have three windows, we need to specify which one is focused. So if I want to look through all the registers, I'm going to focus reg, and now my focus is on the register window. So if I move the arrow keys or scroll, it'll start scrolling that window. And for now, we can focus on the assembly window. And once we're here, we can see all of the things. So let's see, we can see in the register window, we can see that T0 contains this value. We can see that A0 contains this value. And as we step through the assembly, we can watch and see, okay, T0 just got the value of A0, which was 5, and it's nicely highlighted the register that's changed here. And we can just keep, remember, if we push enter, we get the most recently executed instruction, so we can go through, we set A0 to 0, and now we can just kind of watch ourselves go through this loop and sum up the values. And again, this is like a complete toy function. And then we can continue and live our lives. And if you're ever curious about what kind of breakpoints you've set, or you lose track of what you were doing, if you type info break or breakpoints, you can see all of the breakpoints that you set in your code. And you can even see, okay, this breakpoint has already been hit one time, and you get lots of useful information doing that. If you don't want to have the register window, but you do want to look at the registers, info reg or info registers or iReg or any of the numerous GDB shortenings will bring up the register window as well. So with that, are there any questions about GDB, simple ones? I know there's been lots of posts on Piazza about it, so now is a good time to just ask some straightforward. And I'll be showing more usage of GDB. What command did you use to open the multiple windows? So I use tmux, so I can show just from scratch. If we go here and I open a new terminal, so here's just a blank terminal. If you type tmux, and this is available on Athena, I'll address the next question in a second. So now I'm in tmux, which you can tell by this green bar at the bottom. And if you want to so there's a couple ways you can do multiple windows in tmux. So you can type Control-B-C, and I know that sometimes, if you're used to using Emacs, that will make a lot of sense, but normal people who don't use Emacs, that's hitting Control and then B, and then hitting C on its own afterwards. That will get you a second window, which you can then navigate between with Control-B and then P, Control-B and then N to go previous and next. Yeah, and David just posted a tmux cheat sheet, which is useful. And if you want to split the windows, I think it's Control-B and then the % will split them vertically, and then double Control-B and then double quote will split them horizontally. And so that's how we get them. And if we're in this state, we can use Control-B and O to jump between our windows. So that's how I got the multiple windows. Yeah, I don't care. And then Ahmed asked, why is this displaying assembly addresses again instead of C line numbers? So because the function, so if we go back to the assembly function, this is implemented entirely in assembly and not at all in C. And so there just aren't any associated C line numbers for this. If we were to set a breakpoint, so if you type delete, you'll delete all your breakpoints. So I cleared the old one. If I now set a breakpoint in demo1, so that's a C breakpoint, and continue and run this. Now if I go here and type layout split, I'll get the C and the assembly. Or if I just want the C source, I can do layout source and I'll just get the C. So that's what's going on. It's just a quirk of the fact that this doesn't have associated C code, and so we don't see C line numbers. Any other questions about GDB, tmux, and that sort of thing?
So layout split is the one that you use to bring up this extra window of the source and assembly and so on, right?
Yes. So layout, if you do layout split, that'll get you source and assembly. Layout source will get you just source. ASM will get you just assembly. And the registers are their own thing, where if you type layout reg, I think, yeah, that'll bring up the registers. But unfortunately, I don't know of a way to get the registers, the assembly, and the C code all at the same time outside of using info reg with layout split.
I have a question. So when we set the breakpoint at a line, right? It displays the address of the, like in this case, breakpoint 2 at 0x86354. But any instruction might have multiple, any like line of code in C might have multiple instructions. So which one does it show?
I believe it shows the first one.
All right.
And it's TU for the person who asked to start the TUI. I think it's TUI enable, not enable TUI. Sorry. I think. Yeah. Yeah, again, there's like 100 cheat sheets out here for GDB and for tmux as well. So if you ever find yourself lost, GDB even has its own inbuilt, its own thing called apropos. So if you look for apropos TUI, it'll actually show you all of the commands that involve TUI. So yeah, this can be quite useful, but it can also be a little bit overwhelming. If you do apropos-v, it'll give you even more information, I think. I don't remember. I don't use it often myself. But if you do find, or if you forget the exact way to type a command in GDB and you don't feel like Googling it, apropos will often be able to find exactly what you're looking for, in addition to a whole bunch of stuff you weren't looking for. Yeah, so that can be quite useful. GDB is extremely well documented as well. So yeah, if you ever find yourself lost, Google is your friend. So now that we've kind of been over assembly and RISC-V and these sort of things, I want to dive a little bit more into the specifics of what you really need to know for the lab coming up. And also, this will be a little bit of review from the document that you've all, of course, as diligent students, read through thoroughly in preparation for this lecture. So this table will, of course, be wildly familiar to you all, and from both 004 and from what you've read. And this is the table of registers. And registers are little locations on the CPU or on the processor, predefined, that it can use to store values. And this is important because assembly operations, if we remember from the assembly code, assembly doesn't operate on memory. It operates on registers. So when we do add, when we do subtract, we're operating on registers. And so what you'll often see as the pattern for writing assembly is we'll have some kind of a load. So we'll load some value to a register. And that value can be from memory, or it can be from another register. And here I'm referring to load in general, not the load instruction. And then we'll operate. So we'll perform some operation on the register. And then if we care about the result of that operation outside of a return address, we will we'll store that register to somewhere, to some location. We'll store that register to some location, be that in memory or to another register. And so that's generally the way things work. And registers are the absolute fastest way to perform any sort of calculation or to access any value. And that's why it's important to use them, and also why we prefer using registers over using memory. So if you remember from the reading, when we call functions, so you can see here that registers A0 to 7. And in general, when we speak about registers, we will be referring to them by their ABI name. Not only is it less confusing, it's just a standard, and it's also the way that you'll write assembly code. These actual numbers are not super important. The only case where it does matter is for the compressed version of RISC-V instructions. And if you want to know more about that, feel free to read up about it. The basic idea is that RISC-V normal instructions are 64 bits, but there's also a compressed version in which instructions are 16 bits, and we use less registers. And the registers we use in that case are 8 through 15. Those are the registers that are available to us. So I think somebody had a question about, why is this S1 register X9? Why is it separated from all of the other S registers? And my guess is that that's why. That we separated from all of the other ones because it's available in compressed instruction mode, whereas S2 to 11 are not. And so that's the idea. So that's for compressed, but outside of that, registers will always be referred to by their ABI name. And so A0 to A7 are used for function arguments, but if we have a function that takes more than the 8 arguments that those registers give us access to, we do need to use memory. But that's this is kind of an illustration of the fact that we don't want to use memory when we can use registers. We only use a memory if we have to. And this column here, the saver column, this is also extremely important when we're discussing registers, caller versus callee saved. And the terms are, I confuse them regularly. Caller and callee, they only differ by one letter. The easiest way that I found to remember them is that caller saved registers are not preserved across a function call. So, and callee saved registers are preserved. What I mean by this is that a caller save register can be overwritten by the function. So let's say I have function A, which calls function B. Any registers being used by function A that are caller saved, function B can overwrite when it gets called. And I think a good illustration of this is the return address, because you can see that the return address is caller saved, and that's important because every function needs to use the return address. So when A calls B, it's important that B be able to overwrite the value in the return address, hence why it's caller saved. And callee saved registers are just are a convention that we use. The frame pointer is important for that reason. And those are preserved across the function call. So basically any register that is caller saved, the function that is making the call needs to worry about those registers. And if they're callee saved, the function that is being called needs to worry about preserving the value in those registers. And again, I regularly confuse the two and find myself returning to this table to remind myself about what they do. And so, if you remember from the reading, all of these registers are 64 bits wide, so they have 64 places where we can put things, and the various data types are made to fit into those 64 bits based on the calling convention. So if we have a 32-bit integer, depending on whether or not it's sign extended, we'll either add zeros or ones to the front of that integer in order to make it 64 bits to put in these registers. So before we move on, does anybody have questions about registers or things of that nature?
I have a question. Can you put a return value in A1?
Yes, this is a good question. So I think in theory you can. The reason why we say A0 to A1 is if a function returns a long, which is 128 bits. So if you remember from the reading, if a function argument is more than a pointer word, and so when we refer to pointer word size, we're saying 64 bits. So if we have something that is twice the size of a pointer word, we can put that in a register pair. And so the same convention holds true for return addresses, where if we have something that's the size of twice a pointer word, we can stick that in A0 and A1 and use that as the return address. I think you'll run into problems if you only try to put something in A1.
Makes sense. Thanks.
No problem.
Why are the registers not like contiguous? So why is like A0 and 1 separate from? Sorry, no, that's a bad example. Why is S1 separate from S2? Why are the A's in between? Like, is there any point in that?
Yeah, so I mentioned this briefly earlier, but there is a compressed. This is a guess. I don't know for sure, but there's a compressed version of the RISC-V instructions, which are 16 bits in size as opposed to 64, and you would use that to try and make your code take less space in memory. And when you use those 16-bit instructions, you only have accesses to registers 8 through 15. So I think S1 is separate from S2 to 11 because they want to make it clear that S1 is available to you in the compressed instruction mode, whereas S2 to 11 aren't. And the reason, I don't know why they picked X8 to 15, but I suspect that that's just they looked at a bunch of code and were like, oh, these are the most commonly used registers. Any other questions?
I had a question. Besides the frame pointer, the stack pointer, and all, I don't know why we would need more callee saved registers, but we do have like a bunch of them.
Yeah, the S1s to 11s, those are just for, I believe, used there for freedom for the compiler or for the programmer to use. So maybe there are certain cases where you want to guarantee that something is still around after your function call. The compiler can choose to use S1 to 11 to do that. I don't have like on hand a specific example of where that's useful, but I'm sure it shows up where having a callee save value is important. But these are basically programmer or compiler's choice to use S1 to 11. And I should note that these floating point registers, they're for floating point arithmetic. As far as I'm aware, you won't see them in this class, and so you don't really need to worry about them. Okay, so we started talking a little bit about function calls, and so with that, I want to move us into discussion of the stack. So this is we're talking about the stack, and the stack. If you've seen it likely before, the reason why the stack is important is it's what keeps our functions organized and sane, and it's what allows and what makes functions work. It's what makes return work, and it's also where often we'll find ourselves saving our registers and things like that. So here I've given just a pretty simple layout of what a stack looks like. And so each of these boxes here is what we refer to as a stack frame. And every time we get, which are generated by function calls. Every time we call a function, that function makes for itself its own stack frame, and which it uses itself, and it does that by moving around the stack pointer. So here's the stack pointer, and this is and it's very important to remember with stacks, we start from high addresses and we grow downwards to low addresses. So the stack grows down always. And so you'll see that the arithmetic for a stack pointer is usually done via subtraction when we want to make a new stack frame in assembly. So the stack grows downwards, and stack frames for a function contain saved registers, local variables. Also, like I was saying, if you run out of argument registers, additional arguments will show up on the stack. And so stack frames are not all the same size. Even though they are in this diagram, that's not the case. Different functions have different numbers of local variables, different saved registers, so on and so forth. And so stack frames will be different sizes, but the two things that you can definitely count on, which are important, is that the return address will always be on the first thing, and the frame pointer, the previous frame's frame pointer, is also going to show up on the stack at a predictable location. So the two important registers here are SP, which, as we discussed, is used for, this is the bottom of the stack, or generally, it's the location of the stack. And then FP is our also important register, and this points to the top of the current frame. And this is important because that means that the return address and the previous FP will always be at a fixed location from the current frame pointer. So that means that if I want to find my return address or I want to find the previous frame, I can always get to those values by looking at the current frame pointer. And the reason why we store the previous frame pointer is to allow us to jump back. So once this function returns, we can move this into FP, and all of a sudden FP again will go from pointing to this stack frame to now pointing to this stack frame. And so we use the frame pointer to manipulate our stack frames and make sure we're always pointing to the one corresponding to the correct function. And that's kind of how things are done. And these pieces of the stack need to be created by assembly. And so everything in that calling conventions document that you read about, that's all enforced by effectively by the compiler. So the compiler adheres to the calling convention, and it's what generates the stack frame. It generates the assembly code that makes our stack frames look correct. So often at the top of a function, you'll see what's called a function prologue. And then there will be the body of the function, and then there will be an epilogue that shows up after that. So this is kind of like what an assembly function will often look like, and we'll take a look at that now. So here I have another function, sum. So you'll note that astutely that sum2 does not have any of these things that it should if it was a proper function. And this works fine because it's simple enough. So it does all of its computations on A0. And so things are good. And we're also not, it's a leaf function. So you'll see, if you see the term leaf function, that's a function that doesn't call another function. And leaf functions are special in that they don't need to worry about saving their own return address or saving really any of the caller saved registers, because they're not going to make another function call, so they don't have to be as careful. Sum then double, on the other hand, is not a leaf function. So you can see here it calls sum2, and so it does need to include that prologue. And so we see here that we are subtracting 16 from the stack pointer. So we're making space on our stack. We're storing the return address for sum then double on the stack. And then we make our call to sum2. And after that, all this function does is it calls sum2 and then doubles the result returned by sum2. And here you can see the epilogue. So we load the return address back into RA and delete our stack frame and then jump out of the function. And so we can run that to make sure it does what we would expect. Here. We can run, so if we run demo 2 or demo 1, we got a result of 15 for the sum, and I'll tell you that demo 2 just calls sum then double, and indeed, it happily doubles the sum returned by sum2. And so a question I have for anybody, what happens if we delete this prologue and epilogue? So what happens if we just have this as our function sum then double? Can anybody predict what's going to happen?
I mean, one thing is that sum then double wouldn't know the return address that it should return to. And so upon calling sum2, that's going to override the return address to be sum then double. So at the end of sum then double, it's not going to return to its original call.
Yeah, exactly. And we can see that that's what happens again. So if we exit out of this and we exit out of this, and we recompile with our broken function, we can take a look at exactly what's going to happen. So we can actually set our breakpoint for sum then double and set up TUI and let it continue. So if we now run demo 2, okay, we're at sum then double. And again, this is an assembly only function, so we're going to want to look at it in assembly. So we'll do layout ASM, layout reg, because it's important what's in the registers in this case. And you'll see that GDB knows a whole bunch of extra information. And so we can see that RA currently, so the return address currently points to demo 2, the plus 18. So it points effectively into the function demo 2. And now we can run, we can just kind of step through our function and see what happens. So we've called sum2, and immediately we can see that the return address was overwritten by sum2 to now point to sum then double plus 4, which makes sense. That's what we'd expect. If we go back into our code, we call sum2, and so sum2 should return to here. And now we can step through, so on up, and then we get back into, whoops, the wrong S. Okay, so now we're here, and now when sum then double returns, exactly as Amir pointed out, it has not restored its own return address, and instead its return address is still the one that was used by sum2, and so we will get into an infinite loop where we just keep doing this over and over and over again, and we'll never terminate from it. And so this is I think this is a good illustration of why it's important to keep track of our caller versus callee saved registers, and hopefully this also shows that you can use kind of GDB to debug these sorts of problems. So let's restore what we had, and we'll go into some other demos to talk about to illustrate. Somebody asked, why are we subtracting 16? That's to put space to get our stack frame. So this is subtracting 16 from the stack pointer. So it's moving it down basically in memory, moving it down so that we now have space for our own stack frame, and then we can stick stuff there. So because at this point, we don't want to override what's at the stack pointer. Why not 4? Is just, well, 4. We need to do 16 because instructions are 64. Yeah, I guess we don't actually need to do 16, but that's generally what you'll see. You'll generally just see. I don't think, yeah, you can't do 4 because you need 8. So 4 doesn't work, but I think you could do you need the instruction size and the size of the register, right? So registers are 64. Yeah, and then so the convention why you usually see 16 is because if we jump back to our document, usually we have the return address and the frame pointer, but we're not doing that here because we're being not super careful with our assembly. So normally, if we look in, I'm sure if we look in kernel.asm, we'll see. Yeah, so if we look in kernel.asm, we see it's also 16. This is generally what you'll see with the compiler. Okay, so now we can go back to this, fix our function, and now we can look at some C code. All right, so here we have demo 4, which is just basically a copy of a main function, like an imitation of the main function. So we have our args, which is an array of strings, and we have dummy main, which takes a number of arguments and the argument string and just prints it out for us. And so that's all that's happening here. It's pretty straightforward. If we set a breakpoint in dummy main, and we hop over, let this. Okay, we let this continue, and we start this. We run demo 4. Okay, so we've hit dummy main, and there's a couple of important things to remember about that you can use GDB for regarding stack frames. So if we type I, so again that's info. If we type iframe, we can see a whole bunch of useful information about the current stack frame. So we can see we're at stack level 0. Level 0 means it's furthest down in the call stack that we can go. And the frame is at this address. The program counter, which is, okay, that's all well and good. We have a save program counter as well. And if we take this address and we jump into kernel.asm and we search for that address, we can indeed see that that address is inside of demo 4, which is exactly where we expect the program to return to. And it was called by a frame at this address, source language C, that's nice to know. And then we have the argument list also starts at this address. Of course, in this case, we have most of our arguments in registers. And then we can even see what the args are. We mean argc is 3 and argv is this address. And if we want to more in-depth examine things, we can look at things like info args, which will tell us information about the arguments to the function. We can look at, but more importantly, we can type, if we type backtrace, or BT works as well, we get a full backtrace of all of the stacks, all of the stack frames from the call stack. So we can see, something questionable happened here. That's when we invoked a system call. Then we get to the user trap function, then to the syscall function, then to sysdemo, then to demo4, and then finally to dummy main. And if we want to investigate any of these stack frames more in depth, we can do frame and then whatever number is along the side here. So let's say I want to look at what was my stack frame when syscall got called. I can go to frame 3. And so now inside of GDB, I'm looking at that stack frame. So if I type info frame, I get this. And here we get a lot more information. We have a bunch of saved registers. We have some local variables. We don't have any arguments to this function. We can see where the program counter, where we're supposed to jump back to, all kinds of things like that. So this is super, super useful for if you're debugging things. And in fact, it's so useful, we make you implement your own version, nowhere near as in-depth as what GDB tells you, but one of the exercises on the next lab will be to implement your own backtrace helper function for use when debugging things inside the lab. And so backtrace is quite useful. And then if we type frame 0, we go back to where we were supposed to be. And if we want to investigate, you probably noticed it's not super helpful. argv is a string, is an array of strings, and so we just get an address for where that's actually stored. And if we want to look at what's in there, there's a couple ways of doing this. The easiest is if we type print, P is for print, and then if we dereference the address, so we go look at what's at an address, we can do that. And as you would expect, we get the first element of that array because when it tries to print a string, it'll go, as C says, it'll go until it hits the null character. So we get foo, which is the first element in that array. And if we want to get more things, we can put in the length. So if we do x and then a number, it'll go up to a certain index. So then we can see both of the strings here. And again, GDB is quite smart, so we can even use argc to print out the whole argument array. And so all of that information is available to you, however you want to get it. So GDB is a super powerful tool.
Why does why does the compiler sometimes optimize out RGC and RGV? That has happened to me before.
Yeah, that just means that the compiler found a more efficient way. Likely, it just got rid of the variable and it's doing all of its operations directly, via register. It might be doing all of its operations on A0, for example. It might just be doing all of its computations on the return address. It's pretty common to see something like that if you if it's a variable that's not 100% necessary. If we don't give you control over the compiler, but if you ever find that in your day-to-day, you can try setting the optimization flag for the compiler to 0. But even then, the compiler will do some level of optimization. Bibek, your hand is raised.
Yeah. What's the address besides that $1 or $2? Like before foo or bar.
Dollar this.
Yeah, so what's that address? Is that the address where foo is?
Probably, yeah.
But then argv points to some other address. Shouldn't those be the same?
So argv is on the stack, and so the reason why, if you look at these addresses, we can see that they're in the kernel. just by the 8000, which makes sense because they're declared statically, right? So in demos, if I go here, they're declared here. And so they're sitting somewhere in the kernel, and they're all car stars. Args or argv is an array of car stars, and so I imagine that each element points to its own string, right? So it's an array of pointers.
I see.
Try and like.
I also have a question about this. The $3 version of the array has, if I look at these addresses, the first one is suffixed by 38. The second one is suffixed by 40. And the third one is 48, which is not uniform, even though the length of each of the 3 arguments is 3. So why are they different?
I'm not 100% certain. My guess is that this is an attempt to align things, right? So to get them on a reasonable alignment. And it is uniform in hex, as people are pointing out.
Oh.
Right. Yeah, that makes sense.
Oh,
yeah,
yes,
16.
I see it now.
Yeah.
Right, thanks.
So you'll sometimes see where things are laid out strangely, where there might be 2 things at strange offsets, and that's just because not everything is naturally the same size. Okay. Any other questions? Okay. We can skip the 5th demo. And so another useful function that we get from GDB are, instead of just breakpoints, there are also watch points, and we can also set conditional breakpoints. So I'll just briefly go over that. We run demo 6. So we can set inside this function, we can watch, so we can set a watch point on, I think here you'll see, yeah, so here you'll see what Luca was talking about, where we see that sum has been optimized out, likely because it's just being put in A0 or something. We can look even at the assembly for this, right? So we can do layout, splits, and yeah, indeed we can see that it's all just being done on the stack, it looks like to me. Oh no, it's all just being done in S0, 1, 3. So here you can see that the compiler decided even to use the call these saved registers. And so we can set things like, we can do watch on I, or we haven't declared I yet because we're not inside the for loop. So if we step through the C instructions, now if we do information for the locals, we see we get I. We can even watch point on sum. So now anytime that sum changes, we'll actually get a notification, so we can continue, and then we'll get a delete here because sum has been removed, so we can't actually watch it. We can even do things like breakpoint on sum2, so this is a conditional breakpoint. Well, let's actually see what is I currently. So I is currently 1. Let's say I think my loop is breaking, and whenever I is 5, well, if I want to specifically debug that case, I can set a breakpoint on sum2 if I equals 5. So now we have this breakpoint, and if we continue along, we'll get to sum2, and we can see that it actually printed out the first couple values, and so we only break now on sum2 if we hit that breakpoint condition. And so that's this can be useful if you want to debug specific edge cases of your code, and watch points can be useful if, for instance, you think that something shouldn't be changing, but you suspect that it is, or you think that something is going wrong every time you change a certain variable. And so that's one usage for that. And the last thing I want to talk about today is structs. Structs are pretty important, and they'll come up in the labs often. And also, I'll talk a little bit about the way structs are laid out in memory. And so a struct is basically it's a contiguous area of memory. So if we have some struct, and we have like field 1, field 2, field 3, when we make that struct, those fields are going to be aligned next to each other in memory. So you can kind of think of this like an array, but F1, F2, and F3 can all be different types. And we can pass them as functions. Usually they're pass them as arguments to functions. Usually they're passed by reference. So here I've made a struct person with 2 integer arguments, and I'm passing a person as an argument to print person, and printing out some of that information. So if we hop into GDB, and let's delete all of our breakpoints and watch points, and now we can set a breakpoint at person, and let's continue and run 7th demo. We can see that now we're here, and so if we type iframe, we can see that we have an argument p, and indeed we can, if we do print p, we can even tell that it's a struct person at this address. And we can, if we dereference it, GDB will tell us exactly what p looks like. It has ID 1215, age is 22. And just to show kind of how things are laid out, we can take this address and we do xg at this address. If we look, I believe it's 8 minus 8. Can't remember exactly. It should be. So if we, again, so we can use this to debug our structures in the code. We can take a look at what's going on with structures this way. So GDB is a super powerful tool, not just for stepping through code, but also for examining all kinds of potentially problematic pieces in your code, and looking at arguments and stack frames and things like that. And this will be hopefully will be useful in the next lab when you have to work with stack frames and with assembly code. So that's mostly what I wanted to talk about today. So with the last kind of 7 minutes of lecture, I'll open it up to any other questions that you guys have.
I had a bit of a tangential question. Who manages the creation of compilers from to get from C to various instruction set architectures? Is that the creator of the instruction set architecture? Is it a third party, something like that?
I believe that it is not the creator of the instruction set. So it's often a third party. So the 2 big C compilers that you'll see referred to are GCC, which is maintained by, I think, the GNU Foundation, and CLang or LLVM, which is its own thing. So I think you can find, I believe LLVM is even open source, so you can find you can find the code specifically that does this. When a new instruction set is released, such as RISC-V, that calling convention document, as well as all of those instruction documents, I think are carefully, but I assume there's like a high level of cooperation between the compiler designer and the instruction set designer. But yeah, short answer is I believe it's a third party who does it, likely with a lot of cooperation from the people who make the instruction set. RISC-V might be an exception where, because it came out of a research project, they may have written the compiler for it themselves as well. I don't think Intel has, for example, has input in GCC or LLVM. Other questions? Okay. Well, thanks for listening in that case, and I guess we can end the lecture here with 5 minutes to spare. So have a nice rest of the